Oh, hello there. I don't think my video is on. Oh, here. Yes, so on the heels of structural induction, we're going to see structural recursion. So structural recursion is very much the same thing, has the same structure, but with the idea of recursion instead of induction instead. So it allows us to peel off one constructor at a time, just like induction also gives you an induction hypothesis that has, one constructor less than the goal you have to prove. They're very strongly related, as we'll see indeed. Well, if you remember the end of lecture 3, we were writing recursive programs, recursive terms to prove, inductive properties. So in the end, they are in some sense the same thing, or virtually the same thing in Lean. Okay. So here's an example. I mean, we've seen examples before. This is a factorial function. And this is another definition which also works, but it has a needless case. You don't need the middle case here, right? If you remove it, this is what you get anyway, because the one case is like 0 plus 1 equals 1 equals 1 times fact 0, which is 1, right? And in fact, we can verify this, right? We can say eval fact of 1, right? It gives 1, so there is no reason to add the extra. Oops, oh, this is a nice video, I think. It's one that's recommended for the course, but it's not what we want here. And let's see. So that often pops up in student homeworks. It's, you don't lose points, you just get a comment from me that it's needless, but you just create yourself more work when you make your definition more complicated, right? So, because you're going to have to do a case distinction on 3 things instead of 2. You're also deviating from the standard induction or recursive scheme, which is that you have the 0 case and the successor case. So that will also cause problems. So typically you want your definitions to be as clean, as simple as possible, because otherwise your proving will get harder. So my recommendation is avoid these needless cases. All right. And now we're going to see something about termination. So Lean doesn't accept functions, if they don't terminate. If Lean cannot determine that they terminate. So here's an example that it doesn't like. So you have the illegal function that takes n. It's by pattern matching here. I could also write it with a lambda. Right, and then that is the same thing. It has the same. No, I cannot write it with lambda. Sorry, because with the lambda, I'm not allowed to do recursion. I can only do plain definitions that are not recursive. So that will not work. I mean that would work, but with lambda here, I cannot. With that syntax, I cannot do a recursive call. I have to do actual pattern matching, so that Lean enables the kind of recursion, support for recursion. Okay, so now we're back to where we were, before we learned something. And then it says, well, it's a very lengthy message that basically says it cannot prove this well-founded. It cannot show that this terminates. Indeed, it doesn't, right? Because illegal of 1 equals illegal of 1 plus 1, which is equal illegal of 1 plus 1 plus 1, and it keeps on adding like this. So that thing, it's not equal 1, it's not equal 2, it's not equal 3. It's well, it's equal itself plus 1, right? It's as if I say x equals x plus 1. This is not good. You're going to be able to derive a contradiction using that. So what I'm going to do is I'm going to derive a contradiction. I'm going to assume that Lean, instead of making this illegal, actually allowed this. And I'm going to do it by simply axiomatizing, illegal. It's just I cannot call it illegal anymore because it is legal now. I'm using an axiom, and also because the name is already taken by this broken definition. So I'm calling it immoral instead, right? So it's legal, but still no good, right? So you see, I say that immoral of n equals immoral n plus 1, so that amounts to, the equation here. And then I have a proof of false, which follows. So you can study it at home, but basically, from this equals that, I mean, we see intuitively this is, going nowhere, right? We're going to subtract on both sides. We're going to get 0 equals 1. And then at the end, we derive false. And we use CC for doing this. So this is one way to write the proof. There are like lots of different ways, but here I'm a big fan of CC, so I've used it twice in that proof. I mean, the proof itself is not so important. I just wanted to make the point that it's very important that definitions are well founded in proof assistant. Otherwise, it's just as if you had an axiom, and axioms are dangerous. If you want an anecdote about how dangerous axioms are, read the footnote at the end of chapter 1 of the Hitchhiker's Guide. And I mean, you might be surprised or annoyed that I refer to the Hitchhiker's Guide pretty much all the time. But I think it really is in your best interest that you read the guide, because one, when you read it, you don't have to suffer hearing my French Canadian accent, and I think that's a huge benefit. And also, it's actually the English looks quite neutral. You couldn't tell it's not a native speaker, I think. But second, the sentences are just more coherent, and I think that's a big win. And you can read them at the speed that works for you. So I would say if you have the choice between the video and the Hitchhikers, I mean, I would, as a student, go for the Hitchhikers. I'm not going to say anything here that's not in the guide, unless it's some kind of joke or that may or may not be funny. Okay. And let's see. Nonetheless, I mean, you're welcome to enjoy the video. Say, we're here to have fun. So already the next section is about pattern matching. So we've seen pattern matching at the top level, like here. But there's also a way to do pattern matching deep inside the terms, right? So it's a bit like it's a term. This whole expression here is a term. So you have that in functional programming languages. You have sometimes called case of, and sometimes called match with. It's a bit like a switch also in, I guess, Java, C, C++, and so on. You can write that anywhere. So here I'm saying, I'm counting the number of elements of lists such that such that P is true. All right, so for the empty list, it's 0. And then for the list XXS, well, I check if P of X is true. And for Booleans here, which is what I use, not propositions, because I'm in a program, not writing a proof. Well, if it's true, which is called TT, then I continue recursively and I add 1. And if it's false, then I just continue recursively. So another way to write this, which I actually prefer, is to say 1, 0. And then I would put all of this in parentheses and say plus, and then you continue recursively. And then you indent properly. And let's see, the first bar is not mandatory. It's kind of or, but we usually put it there, right? And there's not only match, there's also if then else. If then else works with, let's see, can we see it? We cannot see it. Works with propositions, right? So you're in some sense matching on the two possible cases of A less equal B here, and in one case return A, in the other case return B. So it's closely related to match. This is the minimum function. And of course, we could define max in a similar way. The wrong case.